Hello, Math 2. This is Mrs. Bricky, and this is Unit 5, Lesson 1. We'll be talking about ratios and right triangles. Unit 5 is one of my favorite units. It's lots of fun. So we're going to be focusing on right triangles for the entire unit. So our first three little example problems have right triangles, and it gives you some information and asks you to calculate one of the side lengths. So we're going to, in this first triangle, we're going to calculate the length of the hypotenuse right here. So it's a right triangle, and we know the two leg measurements, so we can use the Pythagorean theorem. So that will be leg squared plus other leg squared is equal to hypotenuse squared. If we add 3 squared and 5 squared together, we get 34 is equal to x squared. And then to get our final answer, we take the square root of x, the square root of 34, square root of both sides of our equation, I guess. And let me get my calculator, sorry. And the square root of 34 is the square root of 34. It doesn't simplify. And, if we were thinking about, how long that was exactly, it's about 5.83. So on this next triangle, we are given that one of the legs is 4 and the hypotenuse is 6, and we're calculating this other leg that is labeled y. So leg squared plus other leg squared equals hypotenuse squared. So on this one, we have to do a bit of subtraction. We're going to subtract the 4 squared. So we get y squared is equal to 6 squared minus 4 squared is 20. Remember, you can't do 6 minus 4. It's 6 squared, which is 36, minus 4 squared, which is 16. So just be careful with that subtraction there. So if we now take the square root of both sides of our equation, we get that y is equal to 2 root 5 if we simplify the radical form there. And let's see about how big that is. That is approximately 4.472. If we were wanting to know the decimal approximation there. All right, in the last triangle here, we have a 50-degree angle. We have a side that is measured 3, and we want to calculate the hypotenuse. And so the Pythagorean theorem won't work because we don't know how long this side is. And this is actually what we're going to work on learning how to do in Unit 5, is if we know another angle in the right triangle and we know one of the side lengths, we actually have enough information to calculate any of the other side lengths in the triangle. It definitely has a set length. And that side length, z, if we knew how to calculate it, would be 4.64 or 4.67, depending on how precise we're being. If it was any shorter than that, then we wouldn't have a right angle right here. And if it was any longer than that, we would not have a right angle. It would start to get to be 95 or 100 degrees depending on how long. So it definitely has a set length, and we just need a tool so that we can learn how to calculate that 4.67. In class, we did an activity where we measured some different ratios in triangles, because ratios are going to help us get our answer. So, for example, this first triangle up at the top, it has a 1 centimeter height, a 10 centimeter width. So its height to width ratio is 0.1, and that was a 5-degree angle. And what we discovered in class is that as that height to width ratio gets greater, our angle also gets greater, but it is not proportionate. And we've talked before in our similarity unit about how angles don't work in proportions. They are not ever directly proportional. And we also talked about that each acute angle has a particular height to width ratio that goes with it. So for example, a 53-degree angle always goes with a 4/3 height to width ratio. So if the triangle maybe got doubled in size, that ratio would be 8:6, but that's the same as 4/3. So 53 degrees goes with that ratio. Um, Height and width, though, aren't very good descriptors. For one thing, because the triangle could be turned in any direction. So we need a little bit better way to describe these sides that we're going to be using in ratios that doesn't require a particular orientation. So when you look at a right triangle, you should be able to always recognize the hypotenuse. We use the hypotenuse in the Pythagorean theorem. So the hypotenuse is the one that is always across from the right angle. So wherever the right angle is, the hypotenuse is the one that's across from the right angle. And it is always the longest side in the right triangle. The other two legs we need to have some names for. They're going to be named relative to a given reference angle. So I highlighted this little angle on the corner, on that bottom corner in yellow. That's going to be our reference angle. So imagine your little feet right there. You're standing here at this reference angle. The hypotenuse is the hypotenuse is the hypotenuse. It's, always across from the right angle. It's always the longest. But the legs we are going to name relative to the reference angle. So the one that is right next to you as you stand at that reference angle, we're going to call it the adjacent leg. Adjacent means next to or adjoining. So the leg right by the reference angle is going to be called the adjacent leg. And the one that is on the other side of the triangle from the reference angle is going to be called the opposite leg. So we're going to have the opposite leg and the adjacent leg. Now you're going to see this symbol in triangles a lot this unit, and that symbol is the Greek letter theta. Theta is used to represent angles in math all the time. It's kind of like having an X, but theta is just like an X, but it's an X that would only be used for angles. So if you see a theta in your diagram, oftentimes it means we're going to try to figure out what that angle is. So on this diagram, you see theta down at the bottom. That tells you what your reference is. So then the opposite would be the one across from it, the opposite leg. The adjacent leg will be the one right next to that reference angle, and the hypotenuse is across from the right angle. Our reference does not have to be down at the bottom though. So if I moved that theta up to the top, and if this was now my reference angle, the lens through which I'm viewing the triangle, that would move the opposite side down here, because this is now the leg that is far away from the angle on the opposite side. Adjacent would now be this tall leg that is adjoining the angle. And then of course the hypotenuse is the hypotenuse. So we're going to just practice labeling these. The reference angle position is very important. So remember to really think about where your reference angle is. So the leg that adjoins to the reference angle is called the adjacent side. The leg that is on the other side of the triangle from the reference angle is the opposite leg. And then the hypotenuse is across from the right angle. Sometimes students say, can I label the adjacent side with an A and the opposite side with an O? I would prefer you to use a 3-letter abbreviation, mostly because the O for opposite looks a lot like a 0 and can end up confusing you. So I would prefer, if you can, to try to use 3 letters for these abbreviations. You don't have to write the whole word though. All right, here's a triangle where our reference angle is up at the top of that triangle. So if we're thinking about, and if you like to, you can label the hypotenuse first, the one that's across from the right angle. The adjacent side is right next to that reference angle, and the opposite side is the one that is across from or opposite from theta. Here's one that's kind of tipped over on its hypotenuse, so that's kind of a different perspective. Our reference angle is down here. The hypotenuse is kind of weird, but since that right angle is up at the top, the hypotenuse is this one that it's laying down on. So where that reference angle is, this is the adjacent leg. And over here across from theta, we have the opposite leg. And so let's go to this one. Our reference angle theta is over here on this side. The hypotenuse is right here across from that 90-degree angle. Since theta is up here, our adjacent leg is at the top, right adjacent to or adjoining theta. And we've got our opposite leg over here on this side. Okay, and you can try to finish that one if you want. All right, so in class we did another investigation where we were each assigned an angle and we used that to find some different ratios. Since we have 3 different sides on our triangle, there are 3 ratios we could talk about. So the ratios we'll be focusing on are the adjacent leg divided by the hypotenuse, the opposite leg divided by the hypotenuse, and the opposite leg divided by the adjacent leg. So those are going to be our 3 focus ratios. So in class, we measured some triangles and wrote down some of those ratios and calculated them. And as we did that investigation and calculating some of those ratios, we, in class, we generated this chart. So this chart has a bunch of ratios, and we investigated different angles, and everyone found some information for their assigned angle. So this chart is telling us that for a 60-degree reference angle, if we divide the adjacent leg by the hypotenuse, we get 0.5. If we divide the opposite leg by the length of the hypotenuse, we get 0.866. And if we divide the opposite leg by the adjacent leg, we get 1.732. Those ratios go with the 60-degree angle. So now that we have this chart constructed, we can use it to get some information about some triangles. So our first question says, what do you know about a triangle with an adjacent leg to hypotenuse ratio value of 0.839? So adjacent leg to hypotenuse, I have highlighted in the chart in green here. Our given value is 0.839. Well, 0.839 is between 0.766 and 0.866. It's between those two values. So that means that the angle in our triangle, the reference angle, is between 30 and 40 degrees. Since the ratio is between those two values, that means the angle must be between those two values. So on this one, our goal is to figure out our reference angle right here. I'll put a theta in there. It gives us some of the lengths on the triangle. So if this is our reference angle, theta right here, then this side would be our adjacent leg. And this one over here is the opposite leg. The hypotenuse is like the path that the airplane is taking. So since we know the opposite and the adjacent, we can calculate that ratio. Opposite over adjacent would be 250 over 1,000. In decimal form, if we go ahead and divide that, maybe you can divide that in your head. That's 0.25. So we're going to look on our chart. This was opposite over adjacent, so we need to use this column. And our opposite over adjacent ratio is 0.25, and that looks like it's between these two numbers. So that means that our angle theta is between 10 and 20 degrees. So we can even use this chart to help us find a side length. This question asks us, what is the length of segment AB? So I'm going to put an X there since that's our value that we're trying to find. Thinking about our reference angle of 20 degrees, that tells me I'm going to be using this part of the chart somehow. Well, the side that we know right here, that's the hypotenuse of the triangle. And the side that we want to know, X, or segment AB, that is adjacent to the angle. So we're going to think about the adjacent divided by hypotenuse ratio. Well, for a 20-degree angle, adjacent divided by hypotenuse is 0.940. Well, in our triangle, the adjacent is x and the hypotenuse is 8.5. So we can fill those two values in on our ratio. So we have x divided by 0.85 is equal to 9.4. If we solve for x, we would just multiply by 8.5. So we get x is equal to 0.94 multiplied by 8.5, and we get x is equal to 7.99, or if we were rounding, we would probably round to 8. So we were able to calculate the length of that side using our chart. So we want to look at this chart a little bit more and think about what patterns you might notice on this chart. So we're going to compare the 20-degree row with the 70-degree row, because you might have noticed that there's some values that are repeated. So when you look at those two rows, you might notice that there's a little switcheroo happening. That's interesting. The opposite divided by adjacent ratio doesn't seem related. They don't have a repeat or anything happening, but the adjacent over hypotenuse seems to have switched with the opposite divided by hypotenuse ratios. Something to notice about 20 and 70 is that if you add them together, you get 90 degrees. So these are complements, we call them. So if you think about a triangle that's a right triangle, if this one is 20, then this one must be 70 because the three angles have to add up to 180. And the bottom corner is, of course, 90. So the reason you see this switch is because we're just switching perspective in our triangle. Another pattern you might notice is that if we look down our chart, this one is decreasing, while the opposite divided by hypotenuse is increasing. This one also increases. You may have also noticed that this last column is the only column that has any values that are more than 1. Everything in this first two columns is a number less than 1, or even we could even be more specific and say it's between 0 and 1. But over here, we start to see some values that are greater than 1. Going back to complements, we notice that switch with 20 and 70. You'll notice that same switch happening with 30 and 60 because they are also complements. So that's just a perspective change in the triangle. And you'll notice that same switch happening with the angles 40 and 50 because, again, they are also complements. And we'll talk more about complements later. Okay, so if I gave you the row for 55 degrees, since 55 plus 35 is equal to 90, I could also use that information on that 55-degree row to answer the ratios about the 35-degree angle. So this adjacent over hypotenuse ratio for 35 degrees must be 0.819, and the opposite divided by hypotenuse ratio must be 0.574. So as you're doing some practice problems, you'll be using this chart. So let me know if you have questions. Thank you.